Welcome to Lesson 6D, Compressible Pitot probe equations. In this lesson, we'll review the incompressible Pitot equation, which you should be familiar with, and then show how to modify it for when the flow is compressible but subsonic. And then we'll derive another version of the Pitot equation called the Rayleigh-Pitot equation for supersonic flow. I'll discuss how to apply it and do an example problem. Here's a picture of a Pitot probe underneath an airplane wing that I took one time when I was flying somewhere. First, consider incompressible flow, where we're trying to measure the airspeed V. Of course, there's some pressure and temperature as well. And the Pitot probe, as you see, is basically a hollow tube. So I'll sketch it something like this, where the inside of this cylinder goes to a pressure measurement device, typically an electronic transducer, or in the old days, a pressure gauge. Let's call this location upstream A, and this location right at the nose of the probe B. At the nose, we have stagnation pressure, so the Pitot probe measures P0, the stagnation pressure. We also need to measure the static pressure P, which is this pressure here upstream, and that can be done by another pressure measurement somewhere near this one, or on the probe itself, which we would then call a Pitot-static probe. I discussed this in my undergraduate fluid mechanics lesson series and in my textbook. This part is the same, but you have a tube within a tube with ports around the outside that measure static pressure. For our analyses here, we'll assume that static pressure P is measured and known. For this case, the beloved Bernoulli equation applies, namely from point A to point B, the stagnation pressure is constant, so PA plus 1/2 rho VA squared equal PB plus 1/2 rho VB squared, where we're ignoring gravitational effects. But we know that this point B is a stagnation point, so VB is equal to 0. And from our diagram here, VA equal V, the speed we're trying to measure, and PA is equal to P, the static pressure. So our equation reduces to P plus 1/2 rho V squared equal P0, since PB is P0. And solving for V, we have V equals square root of 2 P0 minus P over rho. This we'll call equation 1, the incompressible Pitot formula, or Pitot equation. This is the one you're used to in undergraduate incompressible fluid mechanics. Now consider compressible flow, but subsonic. Beloved Bernoulli does not apply since the flow is compressible. In other words, because rho is not a constant. So what do? Well, there are some compressible forms of the Bernoulli equation which can be used for this application, or we can analyze this using our equations for compressible flow. Again, we draw a close-up of the nose of the Pitot probe, where we're trying to measure speed V. Here I'll call it V1. We have some Mach number, density, pressure, etc. Pressure here is the stagnation pressure, which we'll call P01. And if it makes it easier to visualize, instead of an airplane, consider a converging duct from a large tank with pressure P0, with our Pitot probe inserted into the duct. The flow here will be subsonic, and the pressure at the tip of this probe is P01, where we'll call the tank pressure P01 as well. Let's approximate the flow as isentropic and adiabatic. Therefore, we can write P01 over P1 as 1 plus gamma minus 1 over 2 m1 squared to the exponent gamma over gamma minus 1. Again, we see a P1. P01 is what we're measuring with our probe, but we also need P1. So we need to measure that, as we said previously, and we also need the temperature so that we can calculate the speed of sound, A equals square root of gamma RT, where T is T1, and from that M1 is V1 over A1, so V1 is M1 square root of gamma RT1. Now we can solve this for M1 squared. We get M1 squared is 2 over gamma minus 1 times P01 over P1 to the gamma minus 1 over gamma minus 1. Now take the square root of m1 squared and plug m1 into here to get an equation for v1. After a little bit of algebra, we get v1 equals square root of 2 gamma r t1 over gamma minus 1 p0 1 over p1 to the gamma minus 1 over gamma minus 1. I'll call this equation 2, which is the compressible subsonic Pitot formula or equation. This is good only when the flow is subsonic. Now consider supersonic compressible flow. I'll ask the students, why can't we use this equation 2 for the supersonic compressible flow case?
Does it give you the square root of a negative number?
Well, no, Dud. P0 1 is always greater than or equal to P1. I'm looking for something more physical.
Well, since the flow is supersonic, wouldn't there be a shock in front of the probe?
That's correct, Sean. This equation is no longer valid because now we have a bow shock in front of the probe. I'll sketch that here. Here's our Pitot probe, and we're trying to measure this speed v1 at Mach number m1, but now m1 is greater than 1. This flow is supersonic. So, as we discussed in previous lessons, you get a bow shock upstream of the nose of the Pitot probe, and it is a normal shock right at the center line. So the pressure measured here is P0 2, not P0 1. Remembering that across a normal shock, both P and P0 change. P2 is bigger than P1, but P0 2 is less than P0 1. So we have to be more careful, realizing that this pressure measurement is no longer P0 1. We have to calculate the flow across the shock first. In particular, we need to calculate P0 2 as a function of P1, M1, gamma, etc., so that we can derive an equation for V1. Well, as I've said many times, it's usually good to use ratios. Here, P1 over P0 2 is P1 over P0 1 times P0 1 over P0 2. And we have equations for both of these from our previous lessons. So P1 over P0 2 is 1 plus gamma minus 1 over 2 m1 squared to the negative gamma over gamma minus 1. That comes from this term, times 1 plus gamma minus 1 over 2 m1 squared, gamma over gamma minus 1, gamma plus 1 over 2 m1 squared to the negative gamma over gamma minus 1. And I need to move this over a little bit. 1 minus gamma plus 2 gamma m1 squared over gamma plus 1 to the exponent 1 over gamma minus 1. This equation comes from P0 1 over P0 2. But notice that these two cancel since the exponents are negatives of each other. So our equation reduces to just this portion of our equation for P0 1 over P0 2 across the shock. Let's rewrite this equation then in its final form, and I'll call this equation 3. This is called the Rayleigh-Pitot formula or equation, valid for a Pitot probe in supersonic flow. Equation 3 cannot be used if the flow is subsonic. Let's verify this equation at our old friend m1 equal 2.60 with air, gamma equal 1.40. Equation 3 gives P1 over P0 2 equals 0.10892. Let's compare this result to the compressible aerodynamics calculator. I already have 2.60 from the previous time I used this, where we got M2, P2 over P1, etc. And now look at this last entry, which is P1 over P0 2, and we get 0.10892, which agrees with our result that we got from this equation 3. So we're confident about our equation, and that always makes me happy. Let me now go through the procedure for applying the Rayleigh-Pitot equation. We measure P1, T1, and P0 2, where P0 2 comes directly from the Pitot probe, and P1 and T1 have to be measured through other instruments. Then we calculate P1 over P0 2, since we know both of these, Then we use the Rayleigh-Pitot equation to solve for m1. And I note here that this equation is implicit for m1, so we need to solve it any way you want. False position method, Newton's method, a software solver, or the compressible aerodynamics calculator. I'll illustrate that here backwards. Namely, for our standard case, we had P1 over P02 equals 0.10892. Here, in the compressible aerodynamics calculator, let's plug in this value and calculate m1 to see if it agrees with our known Mach number. Namely, let's copy this guy, and instead of m1, we pick P1 over P02 as our input. I'll paste 0.01089, the value that we had here, and calculate, and indeed, we get 2.6 as our Mach number. And I got the same number using the false position method, again verifying our equation. Now let's do an example problem. A fighter jet is cruising at supersonic speeds, and at the altitude where it's flying, the air pressure and temperature are known, and the Pitot probe measures 52.32 kPa. Let's calculate the Mach number and the speed of the aircraft. I typed out the Rayleigh-Pitot equation here. At this T1, we can calculate A1 as square root of gamma RT1, and we plug in our numbers along with the units as usual, and we get 295.076 meters per second. From these two values, we get P1 over P02 equals 0.413991, since both of these pressures were measured. Finally, to calculate the Mach number, we solve implicitly for m1 at this P1 over P02 value. I used the false position method and got m1 equal 1.203, and I'll quickly verify that with the compressible aerodynamics calculator. Namely, we set P1 over P02 to 0.41399 and hit calculate, and we get m1 as 1.2027, which again agrees with my calculations. This is our answer for Mach number. To get the speed of the aircraft, we know that V1 is m1 A1, and using more digits for Mach number 1 and using our A from here, we get 354.9 meters per second to 4 digits as the speed of the aircraft. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.